Hello. Welcome to our 12th lecture. Today we will have the Q&A of good coding practices and design recommendations for FPGAs. Second of this one. So let's have a quick video and audio quality check and then I will start. Let me check the voice level. It looks good. But it would be nice if one of you can validate this, approve this. Do we have any moderators today? All right, it looks good. Then let's start. This is the first slide of our presentation. Next one is our agenda. Let me set up my video on top right. Yes. Today, as of 22nd of December 2024, we are having the 12th lecture of in English FPGA from zero to hero series. So our agenda is as follows. We will check if we have any questions and I will try to answer them. If no questions are on the as long as there are no questions, there is no questions on the chat window, I will review previous lecture slides. Also, I added 3 more slides to them. Some code examples regarding VHDL synthesis attributes and if generates, for generates statements. So let me divide this second screen into 2. Okay. Now for now I cannot see any questions. Then I am reviewing. I am starting to review 11th lecture slides. As I mentioned, it also includes this presentation includes 3 more code examples, VHDL and Verilog code examples regarding the previous topics. So let's start with the first one. First, good coding practice and design recommendation we discussed last Wednesday. It was minimizing number of clock domains. So we discussed, we recommended to keep the number of clock domains as low as possible. And we mentioned ideally having only one fast core processing clock is preferred and it is preferred to apply clock domain crossing for lower speed clocks as early as possible. So as I mentioned, if you do some operations, some DSP usage, some flip-flop usage, some lookup table usage in different clock domains, and if you try to apply clock domain crossing after increasing fanouts in those clock domains, lower speed clock domains, then it is not optimal. Instead, having one fast core clock inside FPGA or SoC and transferring all other lower speed peripheral signals to that clock domain as early as possible, that matters and improves the actually placement and PNR result, placement and routing results. Also, timing is closed in an easier way. Of course, you need to take care of some design complexity issues. You need to sometimes pipeline them. You need to sometimes add some extra pipeline. You need to sometimes divide some logic into some 2 or 3 steps. But as long as 1 or 2 clock cycles or a few more additional pipeline delays are not a problem for your design, this is a much more stable way, because then you don't suffer from having multiple clock domains in your design, and you are not supposed to do clock domain crossing for large vectors using FIFOs or handshake mechanisms. Also, we gave an example, as you see here, for some target clock domain core processing clock speeds for different Xilinx FPGA SoC families. So 150 MHz core clock for Vertex 5 family, whose processing technology is 65 nanometers. So as we also explained nicely that it is not perfectly linear, but that decrease of transistor size and increase of target clock frequency is a little bit relatable. So like 30 something percent increase, as you see from Vertex 5 to 6. Also there is like 38% decrease in the transistor size processing technology from Vertex 5 to Vertex 6. Also they are like they are also relatable from Vertex 6 to 7 and for the others. So we our target FPGA core clock speed here for Vertex 5 150 MHz, for Vertex 6 200 MHz, for Vertex 7 300 MHz, for UltraScale Plus, for UltraScale 20 nanometer processing technology 400, for UltraScale Plus 16 nanometer technology 500 MHz, and for the newest one, adaptive AMD Xilinx Versal SoCs, whose process technology is 7 nanometer, TSMC FinFET, as far as I remember, more in detail. So for that one, the target core clock speed is 800 MHz. Next one was reducing high fan-out nets. So recommended to reduce high fan-out nets as much as possible. Also, there are different techniques to handle high fan-out nets. As an example, I provided a link from Xilinx high fan-out net optimization techniques. Also, I shared this presentation on LinkedIn, so you can download it, click it, and check this nice website link and examine the details. Also, we mentioned to reset signals only when it's a must. It's when it's a must-have. We discussed that one more in detail in 10th and 11th lectures, whose topic was reset architectures. Then for the other one was mastering your FPGA device family by reading its documentation and applying some code edits, compile it, and check the compilation results cycles. In that way, you will improve your skills regarding your FPGA device families, resources, built-in resources. And in that way, of course, the results will be much more optimized. So Fmax, maximum frequency, will increase, and resources you are using will be relatively low compared to writing codes whose target is not the FPGA device family you are using. So you need to improve your coding techniques such that you have some FPGA vendor generics and also FPGA vendor family generics, such that you can write plain VHDL or Verilog code such that results, resource usage, and maximum frequency will be much better. Next one was preferring block RAMs to distributed RAMs, also known as LUT RAMs. This also improves your placement and routing, and also affecting timing results as well, because if you don't use block RAMs, then distributed RAMs are used. Distributed RAMs are the read-only memories implemented inside Xilinx slices and Altera's ALMs, adaptive logic modules. So those LUTs, lookup tables, are implemented as if they are RAMs, random access memories, and if, for instance, outputs are also registers, those flip-flops inside slices or ALMs are used. The only example I have seen in the past to prefer LUT RAM, of course, if all the block RAMs are somehow used by the legacy design you captured from someone, this is also a probability, but my observation was in one of the projects I was working, some faster clock operation was required, and using block RAMs for that specific FPGA family, it was not possible. So we on purpose preferred using LUT RAMs inside the super logic region, such that the algorithm is implemented with a faster clock. So also in Xilinx trainings, Xilinx online trainings, it is recommended to use LUTRAMs for some local logic implementations which requires faster clock speeds. So this is also recommended, one of those Xilinx online AMD Xilinx online trainings. It was something, I think it was one of those ultra fast design methodology trainings. Here, and as an example, I provided usage of RAM type attribute to force preferred RAM type. And as I promised last Wednesday, I am providing some code examples in the next slide with some comments as well. This is for Vivado, AMD Xilinx electronic design automation tool, as many of you knows. Here it's a RAM style, also ROM style attributes. Let's read the comments fast. Actually, it says RAM style controls, this RAM style VHDL synthesis attribute controls how the Vivado synthesis tool infers memory. Accepted values of values are block, as we discussed, block RAMs. It instructs the tool to infer RAM B, block RAM type components, and distributed. Distributed is instructing the tool to infer LUTRAMs, as we also tried to explain. By default, the tool will select which reads random access, just a second, reads random access memory. What was the ROM? Read-only memory. ROM was read-only memory. RAM is random. Am I remembering it wrong? Random access memory. Random access memory. ROM is read-only memory, but ROM. Let me check. RAM is random access memory. ROM is same kind, but read-only one. Yes, read-only memory. It stands for read-only memory. By default, the tool will select which RAM or ROM to infer based on heuristics, actually its own adaptive algorithms that give the best results for the most designs. So unless you specify it, actually it is similar for many other design approaches in FPGAs or SoCs as well. Unless you provide some constraints, unless you give some provide some attributes to EDA tools, electronic design automation tools, they give those calls, they make their own decisions according to their adaptive algorithms. So you need to specify and direct the tool according to your needs. So here, also there is a remark: place this attribute on the array that is declared for the RAM or ROM. VHDL example you see below. First, RAM style attribute is defined. Attribute RAM underscore style string. This is a string attribute. This kind of VHDL synthesis attributes are strings. Their types are string, let me say. And then you provide attribute RAM style of myRAM. myRAM signal here is defined before. It's a two-dimensional array. And then you provide a colon, and signal is distributed. Here distributed RAM is preferred. Also, as you see below, for these kind of VHDL synthesis, VHDL or Verilog synthesis attributes, by the way, is little bit dependent on the tool. So for Vivado, it is little bit, could be little bit different. For Quartus, also Libero, you need to check those tools guidelines. Since this is a Vivado example, as you see, accepted values for these attributes are block and distributed. So, also there is a ROM, read-only memory example. Again, you define the attribute ROM style this time. So attribute ROM style of my ROM. Again, preferably two-dimensional array. Signal is distributed. Also distributed is preferred for ROM1. Also you could use, you may prefer this block. Verilog example is also as follows. That's parentheses star RAM style equal distributed. Again, star, you close the parentheses, and then you provide that RAM array information. Since those enumerated types are not possible in Verilog, this kind of approach is followed here. So data size, we don't know the data size, it's a generic value. Let's say it is by default 32 bits. So 32 bits of a RAM array or ROM array. Also the size is 2 to the power address size number 1 minus 1, sorry, down to 0. So if address size is, let's say, 10, then there will be 1024 different random access memory locations where each RAM element size is 32 bits if data size is 32. So by the way, quite similar approach, kind of definition will be here for the VHDL example, but I haven't provided my RAM enumerated type definition here. Next one was, next remark we had regarding good coding practices and design recommendations were preferring digital signal processing cores, DSPs, to LUTs plus flip-flops as much as possible, once again, because digital signal processing blocks are ASIC elements which are very well optimized and packed inside FPGAs or SoCs to do multiplications and many other arithmetic logic operations. As you see, there are some pattern detection, also subtraction, AND gating, OR gating, some different gating of input signals, multiplication, summation, subtraction, also multiply, add, subtract, and do some different kind of logical operations are possible. there are different stages of registering. These are quite important because these registers are packed inside these digital signal processing units. So there are some pre-registering stage, as you see here. Also, there is the second level of registering. There is a second level of registering stage here. Also, there are output registers at close to the output ports of those DSPs. So proper usage of these DSPs, actually preferring DSPs to LUTs and flip-flop combinations, relaxes your timing and improve your resource usage dramatically. Of course, as I mentioned, this depends on your design requirements as well. If you are not supposed to do any DSP kind of operation, then using lookup tables and flip-flops sometimes could be fine as well. But most of the time you do some pattern detection, some comparisons, some gating stuff. So as long as you can use DSPs, use DSPs. This is my recommendation. Another Vivado example I provided here. Also, there are some comments. Let's read the comments as well. So Vivado, actually AMD Xilinx says, use DSP for 8 attribute allows user to control how synthesis tool deals with arithmetic structures. Accepted values for this attribute are yes and no. By default, multipliers multiply and add, multiply and subtract, and multiply accumulate type structures go into DSP 48 or 58 blocks if possible. Exclamation mark. This part is important. This is by default. This is happening by default, but you need to, your plain VHDL code needs to follow design guidelines of Xilinx in this case, or design guidelines of Altera or microchip for that particular FPGA you are using. For instance, let me give an example. If you are using DSP 48 blocks in, let's say, UltraScape Plus family, and if you are using asynchronous resets in your DSP implementation code, then this by default behavior is not possible because Xilinx DSPs, digital signal processing units, does not have any built-in asynchronous resets. And then tool will not prefer DSP 48 or 58, but tool will use some lookup table and flip-flop combinations. Then you will not be able to benefit from that highly optimized, higher speed DSP blocks. So that is why I add this if possible warning. You can this plain VHDL code writing is also a good coding practice and design recommendation in general. Otherwise, if you always use instantiate components from IP library of your EDA tool, then your code will be too much technology dependent. This is not an ideal way. Instead, using plain VHDL, just the VHDL code like this, and adding some vendor and family generics and implementing this stuff without using some technology dependent component instantiations This is a much better way, such that that code will be reusable in different projects with different FPGA vendors and families. Otherwise, you need to do different. Yeah, for instance, let me give an example. You can optimize your signal processing, one of your signal processing components. You can optimize it for 10 different FPGA families by using some if generate statements and selecting required processes according to that FPGA family generic. But also you can do same stuff by using 10 different VHD files. So this is the second one, is not recommended in general. So plain VHDL, not using technology dependent components as much as possible. This is also an important coding practice. You can also support different vendors, like little bit different coding techniques for Vivado, for let me say Xilinx, for Altera, and for Microchip, and for other FPGA vendors. You can support, for instance, with one VHDL code, you can support 40, 50 different FPGA families. Otherwise, you need to, you will have that 40 different VHD files, and most of the time they will not be reusable by others easily. Because, by the way, as the tool version changes, as Vivado gets some updates, as Quartus gets some updates, that technology dependent components, port names, and port types are a little bit changing as well. So it is really tough to maintain those codes. Instead, optimizing using plain VHDL or Verilog or SystemVerilog and optimizing your designs accordingly, plus benefiting from CI/CD cycles, continuous integration, continuous deployment cycle, to check if there are any unexpected issues, is much preferred. Much, let me say, much more team friendly, designer friendly, verification friendly. This is like a conclusion after 15 years of experience. Of course, you may prefer the other way as well, but in my opinion, my recommended way, the way I recommend it is much better, and save some time. Outputs are more reusable and more readable. So let's continue. Yes, we explained in detail this if possible exclamation mark stuff. Next, adders, subtractors. Yes, adders, subtractors, and accumulators can also go into these blocks, but by default, they are implemented with Fabric instead of using DSP blocks. Fabric means here lookup tables and flip-flops inside the slices. If this attribute is not specified, default behavior is for Vivado synthesis to determine the correct behavior. So it uses its own adaptive algorithm to decide, to optimize resource usage, to optimize timing, optimize the timing, to close the timing actually. But as I mentioned, if your coding styles are not fitting to the specific family you are using, then the tool may not optimize it correctly as well. So actually tool cannot optimize it because your code style is against your built-in resources. Actually, this is not the fault of the tool, but yours, because you are not writing code which is recommended by the design guidelines of your FPGA family. Next, it says this attribute overrides the default behavior. Yes, this one overrides the default behavior and forces these structures into DSP48, 58 blocks and is placed in the RTL register transfer level on signals, architectures, components, entities, modules with the following priority. Priority is highest priority is signals, medium priority is architectures and components, and the lowest priority is modules and entities. Of course, if, for instance, there are not available, if there is not any available DSPs, then tool cannot fit, cannot use those all of the attributes properly. Sometimes it can, but whenever it cannot, those are provided in the warnings as warnings inside the logs. Here, first the VHDL code example attribute use underscore DSP for 8 string. Then for this PREC signal, this is the output register of the that DSP code implementation, and you provide attribute use underscore DSP for 8 of PREC, P underscore rec signal is no. For instance, in this example, DSP usage is not preferred, but as you also see at the top, yes is also accepted for this attribute. For the Verilog example, again use underscore DSP for 8, yes, then you provide the module. Here example is a little bit different. These are from Xilinx, by the way. So here the module test DSP usage is overridden. So last one was using compact processes. So trying to keep process statements as short as possible and as dedicated to some jobs, some tasks as possible. And using generate statements, which improves, as I mentioned before, readability and reusability. Too long processes are hard to be optimized by compilers. So the EDA tools like Vivado, Quartus, or Libero. There are many reasons for this actually, but one of those is they usually contain unnecessary dependencies, so tool is getting confused how to optimize it. Fanouts are most of the time unnecessarily increased as well. So try to keep the processes as compact as possible, such that your EDA tool will optimize the RTL and output higher frequency, better Fmax, maximum frequency results with less resource usage. I mentioned here again, use FPGA vendor front/family or family specific coding styles. You can benefit from the templates in EDA tools and design Altera or Intel Altera or AMD Xilinx design guidelines. Last one, last sub, not let me say topic, but last remark regarding this topic was benefit from if generate, for generate statements and for loops. Be careful about range and vector limits. I have a code example here regarding that one. About that one, we have a like behavioral of this is the name of the architecture. An architecture named BHV, behavioral. Entity name is just an e.g. example algorithm. And we have a signal just among many. I just mentioned that 3 dots here. So there are some also, of course, other signals, constants or attributes there. But we have a my signal. We have a signal called my underscore signal, whose size is 8 bits, 7 down to 0. As an example, we have a for generates and 2 if generate statements inside that for generate. That G underscore algorithm generate statements label. This is the label of generate statement. So for k in my underscore signal tick reverse range. So this means this for loop will start from 0 and go to 7. So my underscore signal tick reverse range, this is equivalent to 0 to 7. Then this for generates will start from 0 and that value k will start from 0 and it will increment until 7, including 7. And if k is equal to 0, there is an if generate statement, then that instantiation 0 ls process, least significant bit process, this is a component, example component. This one will be tight. So this is the instantiation of ls process when k is equal to 0. If k is greater than 0, there is another if generate statement. Then that non-ls process component will be instantiated actually 7 times, because when k is 0, this one will be instantiated. Otherwise, 7 times this one will be instantiated. What are the benefits? Yeah, if you wouldn't use this for generate statement, you would generate, you would write that port map of ls process one time, but you need to do this port map stuff for non-ls process 7 times. But this kind of for generate, if generate statements shortens your code length, number of lines you have. Also improves the readability because you understand how these connections are actually constructed. Also here just as the bounds of this upper level for generate, we used this signals reverse range, but also it is possible to use sometimes component generics as well. For instance, if you would like to optimize an digital signal processing algorithm for ultra scale plus family, then you use you use a string FPGA family generic. Then depending on its value, you add, you call some processes which are optimized according to the design guidelines of that specific family. So this is also a very, very good coding practice, as I tried to explain for DSP and RAM attributes in previous slides. One remark regarding VHDL 2002 and 2008 difference. Actually, this if generates statements are supported by both VHDL 2002, VHDL 2008, and VHDL 2019. But else if generate statements are only supported starting from 2008. So you can use if generate statement in both. Also it is supported in VHDL 93, sorry, 93 I mean 1993. But if else if generate stuff is supported starting from 2008. You can, yeah, by the way, these stuff are not logic. This is an important remark. Those generate statements, these are decided after elaboration. So like constants, these stuff are not providing any logic. So this is after you click synthesis, one of the after the syntax check, elaboration stage starts. All those construction of your VHDL Verilog or SystemVerilog design is handled. So these stuff are not generating any logic, but saves you to add some recursive codes and helps you to provide actually build your code infrastructure according to some constants, some bounds like we have here. We illustrated here also some for some generics. Yeah, this is the end of today's recap. Also we went through some examples. Now I will check if we have any questions today. I think majority of people are on holidays. Today I couldn't see any moderators as well. If I cannot see any questions, I will stop the stream. All right, we don't have any questions. So thanks a lot for listening. It will be appreciated if you can like the stream. If you are watching it live or if you watch it later, I will be happy if you can like the video. Thanks a lot. Have a great Sunday. Take care. Bye bye.